bigger, make this smaller. There we go. So the start of this section is going to be ANOVA. We're going to do ANOVA for like a while. Because we're going to do ANOVA and then MANOVA, which is the multivariate version, and ANCOVA and MANCOVA. So we're going to cover lots of variations on a theme here. But I'm going to start by explaining just like the idea of ANOVA, and then we'll talk about the R stuff. So I got really cute on what ANOVA is. It's an analysis of variance. So that's what it stands for. That's why it's a cute acronym for analysis of variance. And is really useful, let's move on, if you have lots of variables. So everything we've done so far has been one variable at a time, unless we've been talking about data screening. So t-test is one IV and one DV, correlations one X, one Y. What if I have lots of IVs? So one or more independent variables. We'll start with one and then do two. And the independent variable has to have groups or levels or conditions, and we'll talk about what those mean here in a minute. And we're going to analyze the difference in means. I know this is called the analysis of variance, but most people are interested in the means. And a continuous DV. So this is like the very short description of like how does ANOVA work, and we're going to break down each part. Okay. So why would I ever use ANOVA? Because as you'll see when we talk about post-hoc tests, you end up doing t-tests anyway. So why do this stupid ANOVA thing first? Well, I still have to use t-tests to analyze two things two at a time. It's called pairwise. But if I do more than a couple of t-tests, I can have a type 1 error. Since that's been a while, type 1 error is rejecting the null when I shouldn't. So saying something happened, something is significant when it's not. That's bad. The first mistake is the worst mistake, so we don't want to say things happened when they didn't. So if I'm doing a bunch of t-tests, I have run the chance of a type 1 error, so I solve that with ANOVA. So one of my favorite quiz questions is why ANOVA when t-tests do the same thing. This is the slide with the answer. Okay, because it's a type 1 error problem. Okay. So why ANOVA? Because it controls for type 1 error. We'll get into how in a second. And now here, like frantic typing. So I'm going to use ANOVA to cover that type 1 error. However, the disadvantage to ANOVA over multiple t-tests is the fact that you do the ANOVA and then you do the t-test anyway. But we're going to control for the error in the t-test in a different way. And we had a very big discussion in our help desk meeting about the simplest way to do this. So I'm going to teach you one package, so the front row will be really happy with me right now. One package and one error test. There are multiple versions of these. We're going to do one theme throughout just to keep it simple. All right. Okay, yep. So breaking down those pieces of ANOVA a little more. So the independent variable, the IV, that's one that has to be dichotomous. Oh, that really shouldn't say dichotomous. You know what that should say? It should say categorical. Dichotomous implies that there's two, right? Girls, boys. ANOVA really should be categorical. It should have three or more usually. So it has to be categorical or nominal, whatever way you want to think about it. I can put people into groups. Or I can use naturally occurring groups. So gender is a naturally occurring group. I can't force you to be male or female. But I could give you instructions or no instructions. So this can be manipulated or not. But it does have to be a group variable. So the reason we covered factoring variables last time was because ANOVAs run much better if you've already factored them. Plus then it labels your output, which makes life a little easier. Why is my computer being dumb? There we go. So the dependent variable has to be continuous. By continuous, I mean you can use interval, those Likert scales, or ratio scales, but it shouldn't be a yes-no sort of thing. That's log regression. So we'll get into log regression, or sometimes it's called discriminant analysis, which to me is a lot easier to understand. Discriminant analysis, it discriminates. Yeah, it's a good label. Log regression, not so much. And your DV, just research design-wise, will be the thing that you're expecting to change. So we're going to calculate averages on these DVs and see if they're different across groups. That's the point of ANOVA. And hopefully they've changed, or we've wasted our time. All right, and I brought a marker today. And there's like 6 today, of course. I was like, I'm bringing one today. Okay. This really kills people when we get into multi-way ANOVAs or multiple variables. This is levels versus conditions. So this is something you want to make sure you have a good grasp on. Or when we get to two-way ANOVAs, you'll be like, what? Okay. So if I have an IV, so I have an example here in a second. Do something really simple. So my IV might be gender and handedness. So nice simple IVs. So we got left and right, male, female. Levels are these things. They're the groups for the IV. So within each IV, if you only have one, you only look at one of them. They're the groups that are within only that IV. Conditions are the combinations. So I have males that are left-handed, males that are right-handed. So these in here are the conditions. So become handedness. So left and right. I have it on the next slide, but not written in this pretty form. So levels are when I look at one IV at a time. So I can look at the differences in whatever we're measuring. Love of cheese, since my examples are always about cheese. Do men and women have different loves of cheese? Okay. So those are levels, that's only one at a time. Do left-handed people enjoy cheese more than right-handed people? I don't know, I would assume, but I'm left-handed. Okay. Conditions, I'd have to look at all 4 of them. So are male left-handed people enjoying cheese more than male right-handed people? So it's the combination of both variables at once. The like lobster claw hands today. Combinations. Somewhere in one class one semester they like wrote down what each hand signal meant. It was very amusing at the end of the year. Where was that? All right, so for example, if I have gender, male and female would be the levels. If I only had gender, right, male and female would be the levels and the conditions because there's only one. But if I have 2 variables, the levels would be male, female, left and right, and then the combinations. I tend to ask people this question too. I'll give you an example and I'll say, what are the levels? What are the conditions? And that becomes important when you're working on analyzing it because the way you test levels and the way you test conditions are different. All right. So it's a little more about types of ANOVAs, or to get into, types of ANOVAs. One-way versus two-way. This wording is slowly going away, which is good, because I think it's confusing. But the word way just means IVs. So I don't know why we don't call them one IV and 2 IV and 3 IV ANOVAs. That would be logical, but we don't. Okay. So one-way ANOVAs are 1 IV, so levels and conditions are the same thing. 2-way ANOVAs, 2 IVs, you have levels out here, conditions in here. 3-way ANOVAs, add another layer, and 3 IVs. Okay. So if you ever see it printed, mostly people only talk about it when they say 1-way ANOVA. Okay. Okay. So to add yet another complication, there are different types of 1-way and 2-way ANOVAs. So the way thing only tells you how many variables there are. This tells you what types of variables they are. And this is going to be important because when we use the function we're going to use is called easy ANOVA. It forces you to tell them which one it is. Okay. So we really got to get the distinction between subjects and repeated measures. Now, I wrote everything they're possibly called. So repeated measures has 3 names. And it's just annoying is all it is. And it's because stats is kind of a conglomeration of social sciences and math and real sciences, so people call them different things. So between subjects ANOVA, or an independent ANOVA, is where everybody's in a different group. Okay. So this is a great example between subjects. I can only be in one of these boxes. All right, this would be me. I cannot be in multiple boxes because I can't write right-handed, and while I think it would be interesting to do mail for a day, it's not a thing we know how to do. Right. So repeated measures, or dependent ANOVAs, or within subjects ANOVAs, are ones where everybody's in all of the conditions. So class is a giant repeated measures design. You take every test, hopefully, right, and every assignment. So you're in every one of those things. A mixed design is mixed. It has one of each, at least. So you might have half of it's between subjects and half of it's repeated. So if I was to compare this class to my baby stats class, that's between. You're only in one class. But on all exams, that's within. You take all of the exams. So that judgments of learning thing that we're doing is a mixed design. So we got one-way and two-way. Obviously, mixed designs can only be two-way or more. You can't have a mixed design with one variable. And the way we're going to describe these, I don't know how to, the best way to word this. I always think of it as windows, but I don't know why I think of it as windows. Maybe because when you're describing the size of something, I don't know. But we're not going to call them one-way and two-way, because that's dumb. It's not informative, is really what I should say. So we're going to use numbers. So if it's two or more way, we're going to use numbers to describe it. So we've got 2x4, 2x3, 2x2x3. If you guys go in Mitchell's class, he loves three-way designs. He will make you do 600 of them. He loves them. Right. We will not do three-way designs because I don't have a death wish this semester. So what it does is it tells me how many levels there are. So I have two examples because this will be clearer if you give me an example. So if I tell you I have a 2x4, what that means is I have two variables. One variable listed here. Okay. So this is an IV and this is an IV. So I've got two IVs. This one's going to have 2 levels. This one's going to have 4 levels. Multiply them together, that gives you 8 conditions. So it essentially would look like this. Right? One has 2 levels, one has 4 levels, so there's 8 boxes. And it's all between subjects. So it said it's a 2x4 between subjects. That's much more informative than saying it's a two-way design. That tells me how many levels there are of each one, how many conditions to expect, and what types of variables they are. So when I ask you to tell me what type of ANOVA it is, I'm talking about both halves. The something by something and the type, between, repeated, mixed. And I think I've gotten better at this. On the assignment, I tell you, like, give me the numbers, give me the type. So it's clear you have to do both. If it's a one-way design, you just say it's between subjects. Because there's no anything by anything. All right, one more example. So a 2x2x3 mixed. We have 3 variables. One's 2, one's 2, one's 3. If you do that math, 2 times 2 times 3 is 12. So there are 12 different conditions, which is just too many. And mixed means some are between and some are within. But I didn't tell you how that worked out. So with mixed designs, usually in the methods section, you've really got to make it clear which one's between, which one's within. So that is how we describe ANOVA. So that gets into the types. The other types of ANOVAs we're going to do are ANCOVAs. Those include covariates, usually continuous variables mixed into an ANOVA. We're going to do MANOVA, which is multiple IVs and DVs at once. So lots of variables. And then MANCOVA is the combo of all 4 of those. But this holds true that there are 3 big types. It's between, repeated, or mixed. And this is a good way to describe them when you're writing them up. Okay. All right. Okay. So getting into like the, not how to run it, that's next week, but the kind of the steps. When I run an ANOVA, I'm really testing a null that's nothing. So the null always means nothing happened because it's null hypothesis testing. This is the Rock'em Sock'em Robots thing again. But nothing happened. So none of the means are different from each other. Okay. Life is boring. Nothing went on. The research or the alternative is always something happened. Something. Magic. It's like a bad gossip column. Something happened somewhere. Stay tuned. Right. And that's the bad part about ANOVA, is that it doesn't tell you what happened. If your ANOVA is significant, right, so we're going to run this ANOVA of whatever type it is. If it's significant, and I know we just finished data screening, or you're finishing it now. Remember, significant means less than 0.05. So this is the big important rule. Data screening 001, this is 0.05. If it's significant, you're sort of left with, okay, what happened? Something happened. What now? Okay. And that's where we're going to do a post hoc test. And post hoc corrections. That's a B. Try again. So if the ANOVA is significant, then we continue and do t-tests, which is why I always ask people, why would I ever do the ANOVA if I'm going to do the t-test anyway? Because if it's not significant, you stop. You don't waste your time doing a bunch of t-tests. Or you fish. Yeah. You stop or you fish. Fishing means like you just try running the post hoc test anyway to see if something happened. So the bad thing about ANOVAs is that I have this extra step on top of post hoc tests. Oh, something that's not in the notes. Sometimes this is called an omnibus test. Omnibus. It's your spelling word for the day. That just means it's an overall test. Overall test. I try to call it overall because I think omnibus just sounds like kind of snobby. Okay. So what is a post hoc test? So a post hoc test is a way to tell what happened. So it's the answer to my question mark. But I'm going to do this pairwise. So pairwise is in italics for a reason. Let me go back to my gender by hand example here. So if I said the ANOVA is significant, great, awesome. I don't know what happens, so I could test if males and females are different. And I could test if left and right are different. Okay. So that would be a test of the levels. That's sometimes called main effects. We'll get into this idea more when we do two-way designs, kind of a preview. Or I could test female left versus male left, female right versus male right. This is considered simple effects, which is really a misnomer because they're not the simplest thing to run. Or interactions. But the key thing about all of this is that they're pairwise. So this is like Noah's Ark, it's 2 by 2. Okay. So I'm comparing one group to another group by level, so male versus female, or by interaction or condition. So this is condition. Add that there. It's still one group versus another. So when you get down to post hoc tests, you're really comparing one mean versus another mean. Whereas with ANOVA, overall, you're comparing all the means against each other. Let's see if anything happened. ANOVA is like throwing something at the wall and seeing what sticks. Post hoc test is figuring out which things stuck. Pairwise tests. There's a couple of types, and they're in Latin to be extra snobby. So a priori tests, prior, are planned comparisons. We're not going to do any of those. And that really means I know exactly what I wanted to do before I started, and I'm only going to do those. End of story. The world is perfect, and I never change my mind about anything. That's not how real research goes. But in a perfect world, they're planned beforehand. Here's what I'm going to do. End of story. Bless you. A posteriori or posterior means that after the fact, it's kind of like, screw it, let's do everything. I want to know what happened. So I'm going to do all pairwise comparisons, or you didn't really plan it. You just kind of did them all. We're going to discuss posteriori tests because that's the most common. This is more about the way you set up your experiment, but they are controlled differently. So if we're trying to solve this type 1 error problem, they do different things. All right. Mostly I have stopped teaching planned comparisons because they're overly complex and like people give you crap when you try to submit them anyway, so that's kind of where I'm at. All right. I'm going to draw you another flowchart because I like flowcharts. So we have our magic ANOVA. I don't know why they're magic, but they are. So there are 3 types. Between, repeated, and mixed. We'll run that Omnibus test or overall test. See if it's significant. If it's significant, then we'll run a post hoc test. So if it's between subjects design and I'm running 2 by 2, they're only in their own groups, which is why we spent several weeks on t-tests. Okay. So the type of test is independent t. Now that's actually kind of simple. In R, remember this would be paired equals false. Okay. Yes, unfortunately it does carry over week to week.
Dang it.
Oh, just get well. We're going to do data screening till the end of time, so be sure you're getting it.
Till the end of this semester.
Yes.
Yeah.
And then hopefully you will keep doing it because there's a reason I'm teaching it to you. There's a whole lot of in the back. All right. Anyways, repeated measures is a dependency. Okay. This is paired equals true. So you have to match the right t-test with the ANOVA. And because of the way that these run, everything runs in log format, where each time point gets its own row. Essentially, you have to know this. So if you run the wrong one, if you're going to run the wrong one, run it this way, because that'll give you more power. But don't run the wrong one. I guess in theory I should say, if you're going to run it the wrong one, run it as between, because then you won't make a mistake. But if you want to find something that's there, run it as repeated. So making sure you understand these variables, which will then allow you to do the right type of test. A mixed design is going to have both types of variables, so it depends on which one you do. And these match over here. But I can't give you one answer for mixed, because it depends which variable are we working with. That's what I don't have as my soda. Oh well. All right. That's the test. Now the correction. So the test itself does not fix the type 1 error problem. This is just physically how you have to run it in R to get the right answer. We still have to correct for running all these tests. So we're still increasing type 1 error. We've got to fix it somehow. We're going to do everything as Bonferroni. It sounds like a type of pasta, but it is not. And I will misspell it probably 6 or 7 times. I have the worst trouble with Bonferroni spelling. But what is the point of a correction? So what corrections do is they control type 1 error. Okay. So what do I mean by that? If I run 3 tests, 3 independent t-tests, I'm increasing my type 1 error. The likelihood of me finding something goes up because I'm running all these tests. So if you do something a bazillion times, this is also the gambler's fallacy, but just pretend with me for a minute. If I do something enough times, I'm likely to find something. Right? And so the way I fix that is I make it harder for me to find something based on the number of times I'm running tests. So Bonferroni is one of the simplest ones. And what it does is it takes the number of tests that you're running and then auto-corrects for you based on that. So it says, oh, you're running 3 tests, I'm going to fix you for 3. Oh, you're running 12, I'm going to fix it for 12. So it controls based on the number of things you're doing. It's not going to be very clear that it is doing anything in the output because it makes life easy for you and auto-fixes P. So what it does is it says, okay, you're running 3 tests, so I'm going to move the finish line, the rejection thing, out further away from you, so it's harder for you to find a significant difference. I don't know that I've used the race car example in this class. No, it's been all about robots. Generally, I talk about this as a race, and we're trying to cross the finish line. P less than 0.05 is the finish line. What corrections do is they pick up the finish line and move it further away. So if it's like in NASCAR, we're like, no, just kidding, run one more lap. Okay. What the program does for your Bonferroni correction in R is it takes that further away finish line and recalculates P. And then, so I wanted to make a note here that is a good thing for you. Okay. That allows us to still use P less than 0.05 as our rule here as well. We don't have to come up with a new rule because it auto fixes it based on this. Okay. So you're still looking for less than 0.05, but it has fixed them for you. Okay. And we'll work an example of a really simple one, and you'll see that the p-values change if you don't correct versus if you do. You do have to know how to spell Bonferroni's name correctly, though, because otherwise it won't run. I have learned this the hard way. Yeah, and then it's written in the notes here. Okay. So we're going to do Bonferroni. There are lots of other ones. My favorite one is Tukey. It's not turkey, it's Tukey. Fisher Hater. You don't have to know these. Everybody have student name calls? Yeah, like I blocked out last semester. There's a bunch of tests. We're going to do just one to make life simple. Okay. And the good thing is it applies to all of these. Chef A, yeah. Chef A is another one. Okay, so everybody got my cute flowchart scribbled somewhere?
Yep.
So we've talked about hypothesis testing, types of ANOVA. Okay. Now we're going to talk about we're sort of going from big ideas to small ideas. So how do I tell if something's significant? We're going to use the F ratio. So there's a new statistical distribution. It's F. Much like cursing, I think. Yes. So before we talked about Z. Z is your standard normal distribution. This is the normal curve for standardized testing. Lots of people. When we talked about T, it's a little skinnier. Z and T are equal if you have at least, I think it's about 100 people. They end up being exactly the same. This is the one that you must do most baby stats on. These are where all the t-tests come from, so degrees of freedom, all that stuff that we had to talk about. If we take T, and we square it, we will get F. So the F distribution is T folded in half. So it's all positive. That's good. Chi-square is also a cousin of all of these. They're all related to each other, and it all comes back to Z, which is a little weird to think about since the normal distribution is not that normal. But if I have at least 100 people, these are roughly equal. I think I have a cute picture. So yeah, F is T squared. So there's nothing negative for F. So with the T distribution, we worked with like n minus 1, or we did n minus 1 plus n minus 1 for independent T, right? And then we could look up a cutoff score, or what we did was we just looked at the P values. The problem with F is now we have 2 degrees of freedom because there's more complicated stuff going on. So we're going to have a model degrees of freedom, which is the numerator, and a error degrees of freedom. And I have another slide here in a minute that explains what those are. So we went from 1 degree of freedom, and we're writing it like this. Now we're going to have 2. Model, comma, error. If you're doing AMA style, it's in subscript, no parentheses. So, like that. So here's some examples of what F looks like. What's really happening is we have to control for the number of levels, or the number of groups there are, and the number of people. So before we were just controlling for the number of people because there's only 2 groups at max with a t-test. So that first degree of freedom is always 1. It's 2 minus 1. So we never had to deal with multiple groups. Well, now we've got multiple groups and multiple people, so we've got to have both. Let's just give you an example of what someone would look like. All right. But the way F is calculated, and I tried to make this picture really cute. I'm not going to show you any of the formulas, just this basic idea. Believe me, you'll be grateful. So here, when I said there are 2 degrees of freedom, a numerator and a denominator, that matches the formula where there's a numerator and a denominator. Now on there it says between groups variance and within groups variance. It's the same idea. I'm going to not call them that. I'm going to call them model and error, because that more clearly tells you what's going on. Model variance is about the IVs. Error variance is clearly error. Traditional books call them between groups variance and within groups variance because that's more how it's calculated. But then people get confused because it's also called between subjects ANOVA and within subjects ANOVA. So the terms get really lit. So I'm going to call model variance and error variance. To me, that makes more sense. Okay. So we're going to come back to this picture. Let me do the first one. Okay. So model variance is red on that picture. And so it's the average distance between the levels or conditions and the gram mean. So I'm going to go back. Each little hump here is a group. And so we want our groups to be far apart. So what I'm doing, and then each little line is their mean. So let's say I have 3 groups of people, and I'm trying to figure out if they're different from each other for whatever reason. What I'm doing is testing if their means are different from each other. And that's kind of what these red lines are supposed to tell you.
Yep.
So we have 3 means. We're trying to see how far apart the means are. So we want them to be far apart. That's the point of the study. You want groups to be different, or why are you doing an ANOVA? It would be bad if they looked like this, where they were very close together. So if all the distributions overlap, your ANOVA is not going to work. Okay, this is bad. You would be unhappy because your ANOVA didn't work. So we want this model variance to be large because it's about the model. It's about the IV. There are big group differences. So small numbers indicate that the means are not very different because they overlap a lot. Large numbers mean that they're far apart, which is what you want. So you want this top number to be big. And correspondingly, we're going to want the bottom number to be small. So you want all the variance to be about the model, not the error. Now the error variance is the yellow one. So it's within each little group. So the idea here is that I have these different groups and I'm trying to see why they're different. The means are different because of something I did in the experiment. So I put them in different condition levels, or I manipulated the instructions. I did something to them. And so I'm the reason they're moving far apart, hopefully. But within each little group, I don't know why they're different from their mean. So within your own little group, why is your score 4 and his score 5? And this other score is 3? I don't know. So we're assuming that we manipulated where the groups are. We moved them apart. But within each group, I'm not sure why they vary. So in a perfect world, each distribution would be very skinny. Okay. Not perfectly skinny because no variance is actually bad. You can't run anything. It will crash and burn. But not too wide. So not platycurtic. Leptocurtic in this sense would be good for you. We're mad. Okay. So what the error variance is an average of the group variances. Because I don't know why they vary within their own group. And so I want that score to be small. Which means I measured my groups well, so we want a small number, and they don't vary a lot. So I'm not getting this sort of picture. Draw this again. So 3 skinny distributions will be good. 3 kind of spread out distributions will be bad. So if you have a large number, there's a lot of error, and that's never a good thing. Smaller numbers, I have groups that tightly cluster around their means. Sometimes this is called individual differences. And while that sounds good, like everybody's their own unique snowflake, in research that's not good. You want them to be the same. Because then you don't know what happened. And you toss it down the street. Alright. So we want a big number over a small number, which will make the whole F ratio much larger. Okay. Oh, hold that thought. Don't want to go there yet. So we want the variance to be due to the model and not the error. And so this number should get big. So you might get an F of 600. That's not unusual. Okay. So these numbers get very large very fast. F's close to 1 are bad. Or lower than 1, because that means it's all error. So the way I think about F is it's an odds ratio at heart. Or what are the odds in the model to the error? And so you always want the odds to be in your favor. This works much better now that the Hunger Games is so popular. So we want the odds to be in our favor. So we want a very big number because that's the odds of us being right, the model being what happened and not the error. If the odds are 1 to 1, that means that the model and the error are the same numbers. And that's not good. If the model's less than 1, that means the odds are mostly that it's error. Which is really bad. So big numbers are good. Even though I really did not like the Hunger Games. If you like that sort of thing, you should read what she ripped it off of.
Which is?
Battle Royale. Yeah, we like to steal things from the Japanese and say it's ours.
Yes, I know.
So, anyways. I feel like our one or two diversity in the room. Yeah. Okay. Okay. So coming back to this. So we talked about degrees of freedom. Oops, that's an R there. Pretend. So I call them numerator and denominator. So the model degrees of freedom is still like groups. It's the number of means. Oh my gosh, with the R's today. I can't spell. It's groups minus one in whatever form. So that might be levels or conditions. It's basically the number of means. Error degrees of freedom is participants minus one plus participants minus one plus participants minus one. So you're out of groups. If you have 4 groups, you do that 4 times. I don't care if you remember these, but I want you to get the idea that it's still n minus 1. So for t-tests, it was n minus 1 or n minus 1 plus n minus 1. For ANOVAs, it's a variation on that theme. Groups minus 1 or n minus 1. So degrees of freedom is generally n minus 1 until we get to regression. And then that goes out the window. But it's basically the number of things that went into that variable. So groups minus 1 or people minus 1 plus people minus 1. And so that's why I have the line at the bottom. I really want you to know n minus 1. Okay, so we're getting towards the end. So we have this whole idea of, we did Cohen's d before, but if I'm talking about my ANOVA statistics, I'm going to add eta squared. If I have a 2 or more way ANOVA, it's going to be partial eta squared. I can't draw eta today. There we go. Eta's so curly. So this is also r squared. It's the same thing. Now, quick hint. Does it say on this slide? It's on one of the other slides. Yeah, I have it in here. Okay. The way this is calculated is it's the model variance over the total. So total is model, oops, plus error. ANOVA is model over error. So the F statistic. So it's always going to be really big. Hopefully, fingers crossed, if you did it right. The eta squared is model over total. So how much variance in your experiment is due to the IV, or the thing that you wanted to have happen, or the model, versus the error. So the F ratio is an odds statistic, so you want it to be really big. The eta squared is more of a proportion. It's not more of a proportion, it is a proportion. It's a proportion of variance accounted for by that variable. Stop with the sound. It is different than D, though. So Cohen's D is a z-score, how far apart are the means. This is from the notes at the beginning of the semester, just a reminder. So it ranges from 0 to 1, because it's a proportion. Small, medium, and large, 0.1, 0.1, 0.09, 0.25. Some people have slightly different rules. These are the ones I'm going to stick with. So how much variance is due to the IV? Not the error. You will get small numbers usually. So if you get 0.6 or something, I'm either going to be like, what did you manipulate? What did you change? Like, what did you make up? Or it's made up data. Okay. So a lot of our assignments are made up data, and so they work really nice so that the assignment will run. Real life isn't that pretty. So on the output in Easy ANOVA, it's listed as GES, which we'll do more next week, as generalized effect size. It's a version of eta squared, but it gives it to you automatically. You don't have to calculate it. Woo. Yes. Oh, you're going to be excited until you realize in the post-hoc test you have to calculate D. So, I am working on a script that will allow you to calculate D, write an R, and I'm really close. Okay, got about half done. And the cool thing about the script is it spits out the stuff in APA style for you. But the t-test won't quite be right because it does them without corrections. So, but it will give you d, at least. All right. So we're also going to talk about power. I feel like we did a little bit of G-power. We done any G-power yet? Have I lost my mind? Okay, so you're going to want to download G-power at some point. It is free. You just go to the interwebs and Google G-power. Okay. University of Dusseldorf are the kind folks who have given us G-power for free. Windows or Mac, although it's a little goofy on Mac. You go down to download and you click Windows or Mac. Yay. Okay. Oh, wow. I can actually see the bottom. That's amazing. So, I think it's because I'm on this larger monitor. But anyway, so what G-power is, and I can't make this window any bigger, is it allows us to calculate power. What we're going to do with G-power is use it to calculate estimated sample size. So power, what really people do with it is they find how many subjects do I need to make this study happen. So it's really important for a thesis or seminar paper or project. How many participants do I need? And if it says 600, you might want to talk to your advisor because you're never getting out of here. Right? But I help with this a lot. Just like, how many people do we need? And then be done with it, right? So for each type of ANOVA, we're going to talk about power. But the other thing I did was on Blackboard, in the notes section with this, I have a G-power document from last semester, so we're going to add some stuff to it as we go, because we didn't cover ANOVA in my other class. But it has different types of tests and what the buttons are that you have to click for that test. So we'll do one way between subjects, and it has right here exactly what you're supposed to fill in for it. So we'll use this as a guide. All right. Now the last little bit I'm going to cover how do I data screen with some caveats. So this really depends on the design type, but accuracy is still screened the same way. With missing data, there's only one dependent variable. And if there's only one independent variable in a one-way design, you have two columns. If they're missing either one, that's 50%. So for ANOVAs, there's not a whole lot of filling it in. Because you would be making up their entire, like 3/4 of their data or more. So generally, you don't fill in what were all those words? You don't generally fill in missing data, you just kind of exclude them. Talking is hard. All right. For outliers, we run into a problem. So what we discussed was Omnibus. But for Omnibus to run, you have to have two columns at minimum. So if we do all between subjects, there's one column. There's one DV. Okay. So we have to do something else. So we'll talk about z-scores when we get to that specific problem. Okay. If you have repeated measures data, keep going with Omnibus because you've got usually multiple DVs. Right. So additivity, that's a correlation thing. Between subjects, there's still one DV. There's nothing to correlate anything with, one column. So I have to move on. With repeated measures, there's a new rule. Okay. It's 999, which means that you have to check the real correlation table, not just the symbols for numbers one. And why is it so high? These are the same people tested over and over again. Of course they're going to be correlated. It's the same person. If the columns aren't correlated, what are they doing in this experiment that they're not answering consistently? Right. And so basically you have to make sure it's not perfectly one, so it will run. This is really the only issue. Okay. And so the answer to why here is because it's the same people over and over again, so we expect them to be correlated, but we can't have it be perfectly correlated at one or it will not run. Okay. You will get a matrix not defined error. Or something to that effect, depending on what day it is. Right. Normal, linear, homogeneity, homoscedasticity are all the same. Okay. We're going to add 2 more tests. We're going to add Levine's test. Oh, I should have written here. Levine's test is for between subjects. Okay. Sporicity or Mockley's test is for repeated measures. Okay. If you have a mixed design, you will get 1 of each. The nice thing is that Easy ANOVA, the package we're going to use, spits those out automatically. Okay. So it will give us Levine's and sporicity, and so when we are running those types of designs, we'll talk about what the heck they mean. Okay. But there are types of homogeneity tests, and we'll cover more in-depth sporicity because it's kind of a weird test. Okay. It's homogeneity's strange cousin. All right, so in the next section we're going to do is examples of each of the following. So we're going to do 5 different examples. 1-way between, 1-way repeated, just to get started. 2-way between, 2-way repeated, 2-way mixed, so you'll get 1 of each, basically. And if you can do all of these, 3-way designs are just usually an extension of these. Which is easy for me to say until you try to do one on your own, usually. Okay. So each one of those, we're going to do power, data screening, ANOVAs, postdocs, effect size, graphs. Graphs is going to be a whole new section as well, and write-ups. You'll be okay. So what you'll want to install between now and next week is Easy. The package is literally Z, all lowercase. And ggplot2. I think we may have installed ggplot already as part of the basics thing, but make sure you have that one. Okay. And then here's my question for the day. Okay. What we tried week before last, was I gave you an example to do, and then I just walked around and answered questions. If I also gave you the answers at the same time, do we like that format? We're going to try one and switch. I can also do one, stand up here and monkey through one. The problem with that is that basically to get through it, you couldn't interrupt. So if something went wrong, you would have to wait. And from personal experience teaching this last semester, watching me do it gets you almost nowhere. Yeah? Yeah. You go, okay, yeah, that looks easy. That was fine. And you start typing, and you're like, So I think what we're going to try is I'm going to give you an example sheet like we did last time, but I'm also going to have the answers in there that you should be getting, because I think that was part of the problem, was that you didn't know if you were doing it right. Right? So I'm going to try to be a little more prepared this time.